Let us discuss this Leibniz rule for differentiation under integral sign. See what we have set U. There is one rectangle E, AB cross CD, which lies inside U. See, U basically a subset of R2, and the very important information is f is a function from U to R which is continuously differentiable on U. This is a very important information we have. So what is given and what we have to prove? We have this function G which is expressed in terms of integral. With the help of this function f of xy, this g of x, which is a function of one variable only, getting x. So this function we have, and we have to prove that if g is equal to this one, then its derivative of g with respect to x. Actually, g is defined with the help of integral, and we are taking its derivative with respect to x. So what will happen? Whatever the function inside integral, we take its derivative with partial derivative with respect to x. This thing we have to prove. So this is a given part, and this thing we have to prove. Getting my point? Okay. So see how to prove this theorem. Actually, we will prove this theorem in three different parts. Part 1, part 2 and part 3. These are independent, most of the, yeah. So at the end, we will combine all these three parts to complete the proof. Getting? So let us prove first part. Okay, let us write the first part. What is the first part? We fix y belongs to CD. Getting? We fix one point y here. Y belongs to CD. So if you fix y, then f of xy is a function of one variable only, x. Then f of xy is continuous and differentiable on closed interval AB. So as I told you, actually f is a function of two variables, x and y, but we fix y. Then it is a function of one variable x, and x belongs to this closed interval AB. So basically f is continuously differentiable, so that's why we can say f of xy is continuous as well as differentiable on closed interval AB. So you know mean value theorem. Getting? A function from R to R, you know the mean value theorem. Basic conditions are function should be continuous, function should be differentiable, and our f of xy satisfies both conditions. So therefore we can use mean value theorem, and the mean value theorem says, therefore there exists theta belongs to open interval 0 1 such that see there is no more space to write. Make a screenshot of it, then we will go further. Such that, what can we write? Such that f of x plus h comma y minus f of xy divided by h is equal to derivative of f. See, y we have fixed, so that's why derivative with respect to x only. Derivative of x plus theta h comma y. Okay, so this is a very important thing we have got. I will call it as equation number 1. Okay, so this thing we have, it is a very important. So in this way we have completed the first part. As I told you at the beginning, so we are going to prove in three different parts: part 1, part 2, part 3. At the end we are going to combine all. See, here part 1 is over, so let us focus on the second part. Okay, in second part, what I am going to do, I am going to calculate g of x plus h minus g of x divided by h. Its value we are going to find. Okay, what is g? In a definition, in a statement of theorem, they have given g. So let us use the definition. So this is equal to, definition says, integration c to d f of x plus h is there. So f of x plus h comma y dy, g of x, definition of g, c to d f of x y dy whole divided by what we have, h. See what I have done, I simply use the given definition of g, nothing else. See, at numerator both integrals are same, so we can take common. Okay, so therefore integration c to d, what will happen, this h I will write here, 1 by h. Okay, so f of x plus h, getting f of x plus h comma y minus f of xy, getting, and dy and integration common h. So this 1 by h I will write here. This is, it is a denominator. No? So I wrote here. But see, these two are same. Getting? Left hand side of equation 1 is same the whatever we have got inside the integral. So therefore I can write, let me write that thing here. So this is equal to integration c to d. What is its value? Fx x plus theta h y, and we have dy. This is equation number 2, a very important thing. So in this way we have completed the second part. So let us start the last part. Okay, we have fx is continuous on E. A very important thing. Initially, I have told you f is continuously differentiable function. So that's why partial derivative of f with respect to x is continuous on E. You remember E means a rectangle which lies inside a U, set U. Okay. So we have fx is continuous on E, and E is a rectangle which is closed and bounded. And E is closed and bounded set. Are you familiar with the result? If you define any continuous function on a closed and bounded set, 101% it is uniformly continuous. So therefore I can write implies fx is uniformly continuous. So the function is uniformly continuous. So that's why what can we write on E? I can mention on E. So I'm taking epsilon. Let epsilon greater than 0 be given. So therefore there exists delta greater than 0 such that simply I'm going to use definition of uniform continuity. You remember definition of uniform continuity? It says norm xy minus uv, if it is less than delta, then mod fx of xy minus fx of uv less than epsilon. Okay, so see, since fx is continuous and it is uniformly continuous, so that's why by definition of uniform continuity I could write it. If this is less than delta, then this is less than epsilon. But a small adjustment I'm going to do, that is, instead of epsilon I'm going to write epsilon by d minus. See, this is statement number 3. This thing we have. Let us go further. You can make a screenshot of it, then we will go further. See, the important things I have kept as it is, so we can use it further. See, after that, what I'm going to do, I'm going to consider mod h less than delta. See, and finally we have to prove that thing, what we want to prove, g dash of x is equal to whatever. See, then see what will happen. Let us find norm of x plus theta h comma y, this one minus xy. Let us find norm. See, norm, you know, we can subtract component wise. First component minus first component, second component minus second component. What will happen if you subtract? X will get cancelled, theta h. Here y will get cancelled, 0. How to find norm? By taking square root of theta square h square plus 0 square 0. So square root cancel, mod theta mod h. Getting? See, but theta we have taken from open interval 0 1, so that's why this is less than 1 mod h. Okay, I will mention the reason, because theta belongs to open interval 0 1, so that's why maximum value of mod theta will be 1, less than 1 actually, less than 1. So therefore we will have this is mod h, and we have already assumed this is less than delta. Getting? I keep it here. See, statement number 3 says if the norm of this 2 is less than delta, then mod fx of xy minus mod fx of uv less than epsilon by d minus c. Therefore from 3 what can we write? Therefore from 3 we can write mod. Getting? Now this is less than delta. What we have proved? This is less than delta we have proved. Okay, so this is my xy and this is my uv. You are getting? And we have proved it is less than delta. So here I can write fx of x plus theta h comma y minus fx of xy less than epsilon by d minus c. Statement number 4. Getting? So I write it properly. Yes, this is statement number 4. Getting? Using this one, using 3, we could write it. After that, so as I told you earlier that we are proving this theorem in 3 parts. Part 1, part 2, part 3. All 3 parts are over. So now let us start the actual proof. Okay, what we want to prove. So let me remove this part and then we will go further. Just a minute. This part is not required now. This part, yeah, we want actually, but there is no space to write then. Let us continue. So I am going to consider, see what I am going to consider? Mod g of x plus h minus g of x divided by h minus integration. We have to prove actually this is c to d fx of xy dy. Okay, so this thing I have considered. We have already proved value of this part is integration c to d fx of x plus theta h y dy minus integration c to d fx of xy dy. Okay, I should mention from 2. From 2 we could write it. See, what can we take common? We can take integration common part. So therefore, mod integration c to d fx x plus theta h y minus fx xy dy. Getting? So see, you can take mod inside the integral. So this is less than or equal to integration c to d mod fx x plus theta h y minus fx xy dy. Okay, so see, already we have proved it is less than from inequality number 4. This is less than integration c to d epsilon by d minus c dy from 4. Getting? So epsilon by d minus c is a constant. We can take common. We can take outside integration epsilon by d minus integration c to d dy. See, there is no more space to write. Make a screenshot of it, then we will go further. So let us continue. So this is equal to epsilon by d minus c. What is integration of dy? It is y simply c to d epsilon by d minus c. We will put upper limit d, lower limit c. D minus c will get cancelled to each other. So this is epsilon. So therefore, actually we had started with mod h less than delta, and finally what we have got, g of x plus h minus g of x divided by h minus integration c to d fx of xy dy, and we proved this is less than epsilon. This thing we have proved. Okay, let me remove this part now. See, therefore, or that is, this is nothing but limit. In terms of limit, we can write limit s tends to 0 g of x plus h minus g of x divided by h is equal to integration c to d fx of xy dy. This thing in terms of limit I wrote. Getting? So are you familiar with this? This is nothing but definition of derivative. So therefore g dash of x is equal to integration c to d fx of xy dy. So in this way we have completed the proof. Okay, thank you. Bye bye.